All right, so we want to draw an accurate sketch of this function. First thing I want to find are the intercepts. So if we set x equal to 0, that would be 0 over -4, which means y is 0, which means our only intercept is at the origin, which is important to know. The next thing we want to find is the asymptotes. We have vertical asymptotes at positive and -2 at x equals positive and -2. And also, if we wanted to find the horizontal asymptotes, remember the horizontal asymptotes are the end behavior of the function. So to figure that out, we want to take the limit as x approaches positive or negative infinity of this function, which is x cubed over x squared minus 4. But as you recall, hopefully, that if the degree of the numerator is greater than the degree of the denominator, it's positive or negative infinity. One or the other, I don't know. So to figure this out, actually what we have to do is long division. So we're going to take x cubed divided by x squared minus 4. So having done that, the question is, what would I multiply this by to get it equal to x cubed? So I would multiply it by x. So if I distribute this x into the x squared minus 4, I get x cubed minus 4x. And I have to subtract that. Doing that, the x cubes go away, and we get 4x. So this is what we're left over. So our new function would be x plus 4x over x squared minus 4. Now, the idea behind this, the reason we take the limit like this, is that if we were to take the limit of this new function, we would get infinity plus 0 now. So the whole infinity plus 0 is what tells us that this function, and in this case it just happens to be just x, that this function is our slant asymptote or skew asymptote. So there's actually no horizontal asymptote in this one. It's not there. It's a slant asymptote when y equals x. It could be different. It could be like x plus 4 or 2x or something weird. I mean, it could really be anything. It could be a parabola. Whatever is not the remainder part of the quotient is your slant asymptote. All right, so the way it is now, I could, what else do I need to find? Domain and range, screw it, we have the asymptotes. I can find those, you can find those, it'd be easy. I didn't do it in the last one, actually. Anyway, I could take the derivative of this function or that function. I'm going to pick that one because I think it will be easier in the long run. So the first derivative, we are dealing with a rational expression. So the first derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared, x squared minus 4 squared. Some distribution. 3x to the 4th minus 12x squared minus 2x to the 4th over x squared minus 4 squared. Some cancellations, and we get x to the 4th minus 12x squared over x squared minus 4 squared. So the question is, where does this equal 0? Well, we can factor out an x squared from the numerator and get x squared minus 12 all over x squared minus 4 squared. So what does this tell us? It tells us that there will be a critical point at 0 and positive or negative square root of 12 and also positive and negative 2. Square root of 12 can be written as 2 square roots of 3. So we have negative 2 square roots of 3. We have an asymptote at negative 2. We have a critical point at 0. we have another asymptote at 2, and we have another critical point at positive 2 square roots of 3. So there's a lot of breaks in this one. But we'll take it piece by piece, no rush. We put this into the first derivative. The square root of 12 is less than the square root of 16, so we can use negative 4 for the lower side. The square root of 12 is also greater than the square root of 9, so we can use negative 3. Let's use negative 1 here, positive 1, 3, f prime of 3, and f prime of 4. So those are all the values we'll use. To save time and not think this through, but please check me. This is positive, this is negative, this is positive, this is positive, this is negative, this is positive. Great. This is an asymptote and that's an asymptote, so I can't find the critical points. I know I have a y-intercept and an x-intercept at 0, 0, so that's a point. This is, if I put 2 square roots of 3 into the function, I should get 3 square roots of 3. And if I put negative 2 square roots of 3 into the function, I should get negative 3 square roots of 3. Great. So we have the critical points, we have the asymptotes, we have the domains of increase. Well, we have the information, we don't have the domains. I'm not going to write them in, just to save time. So they break at negative 2 square roots of 3, negative 2, 0, 2, and 2 square roots of 3. That's the important stuff. So next we need to find the second derivative. Now to find the second derivative, I'm going to use this version of the first derivative. So the second derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, which we would have to use the chain rule, times the derivative of the inside, all over the denominator squared, which is x squared minus 4 to the 4th. And this is going to equal 8x times the quantity x squared plus 12 divided by x squared minus 4 cubed. So another project that I want you to do and have done when you come back from break is to show all the steps from here to here. There's a lot of algebra in there, and I want you to do it. Okay, so now the question is we have to find inflection points. Remember, inflection points happen where the second derivative is 0 or undefined. Well, it's going to be 0 at 0. This will never equal 0, so we have an inflection point at 0. We also have an inflection point at positive and negative 2. So we need values to put into the second derivative, so let's use negative 3, negative 1, 1, and 3. Using substitution, if we put negative 3 into the second derivative, this will always be positive, that's negative, and this would be 27 minus 4, negative 27 minus 4, which is negative, which means this whole thing will be negative. And in a similar fashion, it will be positive, negative, and positive, which gives us concave down, concave up, concave down, and concave up. Cool. Did I write increasing, decreasing? I didn't. This is increasing, decreasing, increasing, increasing, decreasing, and increasing. Granted, that's not too difficult to tell. With the plus and minus, it's the first derivative. It can only be increasing or decreasing. So anyway, cool. Those are asymptotes. There's our intercept again. So I don't want to solve for that. If you would want to, remember, put 0 into the original function. because you put values into the function to get points. And we want a point, so we want to put this x coordinate into the original function. Anyway, that's a whole lot of information. Let's plot it. I need graph paper right there. You, come here. And like that. Okay, cool. So some stuff that we have the x and y intercept at the origin. We have a vertical asymptote at -2, and we have a vertical asymptote at +2, and we have a slant asymptote at y equals x. And I should finish that. You, bit father. There you go. You, stretch. You, stretch. Great, cool. There's the asymptotes. Again, notice we have an intercept on an asymptote. That's fine. The horizontal or slant asymptotes only tell us about the end behavior of the function. So, no biggie. Okay, what else do we have? We have the intercept, we have the asymptotes. Now we start plotting some critical points. So at -2 square roots of 3, -3 square roots of 3. -2 square roots of 3 is negative the square root of 12, which is between 3 and 4. So between 3 and 4 is the x coordinate, and then 3 square roots of 3 is going to be similar to the square root of 27, which is a little bit more than 5. So 1, 2, 3, 4, 5, a little bit more than 5, right there. So at negative square root of 12, negative square root of 27, and positive square root of 12, positive square root of 27. It's going to be something like that. So our increasing, decreasing, this domain is increasing. This domain is decreasing. This domain is increasing. This domain is also increasing. This domain is decreasing. And the rest of it is increasing. Wow. Okay, cool, great. As far as concavity goes, all of this is concave down. This bit is concave up. This bit is concave down, and the rest of it is concave up. Which begs the question, did I do this right? Yeah, I did. Okay, cool, cool. All right. So now we can start sketching it in. The first part is increasing in concave down, so that's going to be the first half of the concave down because that's the increasing part. And we're going to be following the asymptote, and then we're going to hit that point. Then we're decreasing in concave down, so we go decreasing concave down. The next is increasing concave up, so the increasing concave up part is going to be that side, which doesn't make a whole lot of sense. I feel it should be decreasing. Let's check. If we put -1 into the first derivative, that's positive, that's positive, that's positive. But if we put -1, that would be 1 minus 12, which actually is negative. So that's wrong, and that's also wrong. These are both negative, which means it's decreasing. So doing your work ahead of time doesn't always help. That's decreasing. That's decreasing. So decreasing in concave up would be the first half of the concave up. So we would follow the asymptote down, keeping in mind that's a critical point, so we have to flatten out there. And then we're decreasing again concave down, so that's the second half of concave down, which looks like that. And then we're decreasing and then increasing for concave up. So it's the first half of concave up, then the second half of concave up. So I would follow the asymptote to the critical point, and then continue the critical point along the asymptote. Whew. Great. So that's what that function looks like. So from this one, what I want you to get is that you can have slant asymptotes if the degree of the numerator is bigger than the degree of the denominator. You can have a slant asymptote, in which case you would use long division, and whatever isn't left over at the end is going to be whatever is not left over at the end. That is your slant asymptote.